All right, so an introduction to DIA data analysis. You got a fair amount from Ben yesterday, but this is a nice little schematic created by Jared Egerton in our lab, and actually in this schematic he's left off the data collection, which happens up here. So in theory, you could set up. You have to make decisions about your sample and what perturbations you're going to do and stuff like that. All your experiment has to happen, but you then once you've got the data, it is sort of a permanent snapshot, and we can argue about like what the resolution of that snapshot is, how good it is, and certainly if in 3 years from now mass spectrometers come out that are way faster and can sample everything at 1 Dalton, which sounds doubtful from what I'm hearing from the instrument vendors, but if that were true, then the snapshot would not be very good, and it would be like looking at a photograph from an old microscope. It wouldn't be so great. But anyway, you get this snapshot, and then you get to generate a hypothesis and select your peptides, do chromatogram extraction from the DIA data, and then peak integration, and then you could do transition refinement based on the peaks. I think Ben definitely talked about that, the ability to sort of go, oh, well, these transitions are getting interference, let me take these other ones. So you could sort of cycle down here, then you do your hypothesis test, and now you could go back and do another hypothesis, right? Like you can come back to this data a fair amount, but the experimental setup is important, and then also just sort of knowing your way around the data and the tools help you to do this cycle on the data. And I don't have this plugged in. So so how do you generate a hypothesis, right? Like what's your hypothesis? And we would say that it's still plenty useful to just have a targeted hypothesis here. You can use DIA data for discovery proteomics, and that's Ben talked about that. It can be it kind of treads the whole range, but and we're going to get into discovery, using sort of large statistical analysis of DIA data for discovery a little bit later. But at this point, we'd say that your hypothesis could come from narrowing down. Say, I want to look at a specific pathway, and that will limit the number of things you're going to look at. You could be investigating a certain complex. I definitely have seen some really great presentations from people who were really just looking at a few proteins in a complex and trying to understand how that complex functioned. Heard a presentation from a guy who spent 20 years, actually a pretty renowned scientist, came to the genome sciences department at UW, and he'd spent 20 years investigating the complex that forms the nuclear pores and how that works to get to take things in and out of the nucleus. So yeah, like that's definitely a targeted use that you could use to, rather than just sort of like, I'm going to take the entire FASTA. You could certainly be focused on certain areas of the cell, using Go terms, and then, or you can definitely you can be focused on specific modification sites. This type of proteomics works very, very well for investigating PTMs. A lot of people using it for phosphorylation and other PTMs. And spectral counting really doesn't work at all for that, because you can't really look. There are too few things that you're counting. So, and then what we would say is, well, some people, well, I just want to measure all proteins. And that's definitely possible. And the tools are getting better and better for that. but that's a much harder thing. We're going to get into how you can do it. But even when we're doing it, we typically will start with some DDA data to narrow things down. So we won't just take a FASTA file and say, hey, let's look at everything. So yeah, so in the DI data analysis workflow, peptide selection could be all tryptic peptides, high responding peptides similar to SRM, peptides in a spectral library, and then we're going to focus on peptides identified by DDA, which actually usually is how you get a spectral library. Is there some set of things that you identify? And now people have started, and we're going to look at one of these. People have started trying to build up these proteome-wide. There's the I think Ben even mentioned it. Maybe they created a library at ETH called the Pan-Human Library. So it's like tons of fractionation collected on their own machines. What they felt they could see, probably really close to that 14,000 proteins that Rudy talked about. And you could go use that to query DIA data. And we're gonna get into talking about how effective that is. Yeah, the Pan-Human Library. So yeah, we're gonna talk about that. The McCoss lab would say that you should do some pre-analysis and understand your samples. And I mean, you could start with Ben's library, but then we're gonna show you a technique where when you finally do the quantitative analysis, you're not necessarily just gonna query everything. So there's the interesting thing about one of the most interesting things that I've seen developing, and we're going to actually talk about this 2015 paper by Bruderer from Biognosis that I thought was very eye-opening, which was that you don't necessarily have to do with DIA, you don't necessarily have to do quantification on the same data that you develop the assay with, right? So you don't have to go to your quantitative runs and just query everything, and so I think tools that use DDA data tend to just go like, okay, you acquired the data, and we're gonna try to quantify everything out of that data, whereas you can do assay development prior to going and querying your high value data, your quantitative data. And then if you do that, then that has an impact on the statistical tools, right? Because you've got a separate experiment. As long as you don't cycle, right? You don't go, oh, I learned some stuff from my quantitative data. I'm going to go back and refine my experiment, and then come back to this data again. We're collecting DDA data to know what we think we can see in the samples, right? And then that all gets searched and everything, and we go, okay, these are the things we think we can see, and we're now starting to feel that, like, well, DDA doesn't see everything that you can see with DIA, and so there are now DIA identification tools that are happening. There's a lot happening, but basically then that's the thing, is that you get better quantitative data out of the fragment ions than you do out of the MS1 ions. And so if you can get with DDA data, you can't get fragment ion chromatograms, right? And there's so you can only quantify off the MS1, right? And so if you think about, like, if I use DDA data to inform myself, and then I go do PRM or SRM, right? We all know that's going to give us way better quantification than MS1. Like the extra level of separation using the fragment ions gives us better quantitative data than MS1. Yeah.
But you can't use mascot for DIA. Why not?
You can't use mascot for DIA. So you got to remember, you can't use mascot for DIA because it's a spectrum search tool, right? So you can't search the spectrum with mascot. Right, so it's a convoluted spectrum, but what we're doing is we're extracting chromatograms out of it to use for quantification. So it's a different thing. We're just going like, okay, we've got comprehensive sampling, of this space, and now we want to go and extract chromatograms, and so it doesn't matter if there's highly convoluted data, with a bunch of ions in there. If we select the right chromatograms, they can have no interference at all and be beautiful, and then we get nice quantification out of it. So that's the idea of why you might want to do a DDA experiment that's just a bunch of replicates to know what you can measure, and then go to DIA data where you're going to get fragment ion chromatograms and quantify out of that. So in the end, you're quantifying out of some peak area, right? Which is a retention time. This is intensity over retention time for a specific fragment in this case. So you could be either it's a precursor ion that's just you've got an MS1, or you get a specific fragment which can have much lower noise. Like a fragment is more selective typically than a precursor. So you're going to have much lower noise, and hopefully we'll keep working on that. Keep going through that. But yeah, so the DDA, and you'll definitely get to see how that works. So and then now there are emerging tools where you could actually do peptides detected from DIA. So you could, and it can be, again, separate DIA runs. It doesn't have to be peptides detected in the DIA runs that you're quantifying on. Could be peptides detected in other DIA runs, and those are likely to match much better to your current DIA runs. And now in our lab, we're typically doing some of these DIA runs. So we have quantitative DIA runs, and then we have other DIA runs that we interleave so that they have very, very similar chromatography. And then we build a library out of these runs. And I think Mike McCoss is going to be talking today, and I think he'll cover that. You can, and so I'm going to start with just a little demo of it's not great. You'd really like to have DIA with no prior knowledge, and you've never seen it before. Like it's who knows whether it's really there, or it's Yeah. So that definitely can happen, but yeah. So it would be better if you actually had a spectrum and a retention time. So knowing a spectrum and a retention time, and you can order synthetics to get you that, and then go back and look. Our lab owns a DNA library from Josh LeBaire, so we express proteins. If we want to look at a protein and we're worried about can we detect it, we'll express it with E. coli. And then that gives us, it's not a shotgun DDA library. It's a library built from expressing proteins and then putting them in water and then measuring the spectra and the retention time. So we have some prior knowledge of where that thing's going to be. And so the first thing I'm going to do is I'm going to do a quick demonstration of Skyline, and you can just watch this part, and then we'll get hands-on in a second. But this is sort of the most naive. Skyline is really quite flexible, and this is, I guess, the most naive way to use it. So yeah, we'll do this like, I have no prior knowledge. Let me go see if I can measure something in DIA, and I'll look over the whole gradient. Yeah.
We've spent the last year looking for this modification, and then you look at the MS2s, and you're like, that didn't actually exist. He used a database, but that wasn't very good. And I feel, maybe you can address this later, but I'm feeling a little unconfident about how to look at MS2s in this DIA world.
Yeah, you won't typically look at MS2s in the same way that you'll look at DDA MS2s, but you will definitely be able to build up the same kind of knowledge where you go like, we had a guy in our lab looking at transcription factors, and yeah, he could look at a peak and go, well, that's not the right peak, So you have to switch to more an SRM mode where you're getting used to looking at the elution profile of a peak, how the fragment ions are co-eluting and what the retention time is. Okay, so people just walking in. People just walking in. These are the flash drives for the course. We're gonna have to share, but at this point, there's few enough people that everybody can have one. And then, but what I'd like you to do is, there's less than 60 gigabytes on here. You're not, well, we're gonna have to share, and they're absolutely packed. They have like 1 gigabyte left on them. So you have to copy these off onto your hard drive. And I've just done that by creating a USB folder in my documents folder. And so that's where I'm going to go right now. And well, actually, first, yeah. So I have a USB folder here. This is my documents USB, and it says DIA intro. And this is what we're going to be looking at this morning. There's that's really hard to see. 2 proteins and DIA tutorial, and the first thing we're going to look at is just this 2 proteins example. I'm going to just show you how to put it together, and then you can just watch this one. So I'm going to start up Skyline, a new instance of Skyline. Just go with a blank document. So from scratch, hope you can see that. The first thing I'm going to do is, since I'm doing DIA, I just go to settings, document settings, transition settings. And one of the first things I like to do when I'm doing DIA is to set up the filter settings. So if this were SRM, if we were working with SRM data, we'd completely ignore this tab, because this is only if I'm going to be extracting chromatograms out of full scan data. So if I'm doing DDA, DIA, or PRM, I need to pay close attention to this tab. If I'm doing SRM, this is completely, leave it the way it is with none. Okay, so let's set this up now. We're going to do MS1 filtering. And now, we added this centroided mode, and now it's our default. And I would say that in a lot of cases, certainly with thermo data and and definitely thermo and Bruker data, definitely I would recommend centroided. But we're gonna go. This tutorial was done with using Orbitrap mode, and it was 3,500 at 35,000 at 200 resolving power. And then we're going to do DIA, which is also Orbitrap, and the resolving power for that was 17.5 at 200. And then, I think this is a yeast lysate sample, so we added this use high selectivity extraction. So if you have something like a cell lysate, you want high selectivity extraction. If you have a lot, going on, if you had, say, purified samples in water, or purified proteins in water, or some sort of immunoprecipitation or something like that, then you might choose to not use high selectivity extraction. And that is just, I showed you yesterday the slide where we started with 10,000 resolving power and it was way too wide. And then we really thought 30,000 would be good, but it turned out to be 60,000 was the best, because it was that was a 3-organism mix. So it was one of your most complex samples. So the more complex the sample, the more you're going to want this high selectivity extraction. And then for DIA, we have to define an isolation scheme, and there are some that come defined here, but I'm going to just go through defining my own, and you don't have to follow along, do this if you don't want it all. And if you fall behind, don't feel bad, because I'm not really intending you to follow all this. But if you can follow, go for it. And then, so in this case, we'll just call this 20MZ opt. So we're going to do 20MZ Windows. Whoops, actually, I'm going to go 800 to 1200. So this is going to be an isolation scheme that covers, 400 to 800. 400 to 800, and it's going to use 20MZ optimization, so optimize windows. So the way I do that is to click pre-specified windows, and then I'm going to calculate them, and I just type in 400, 800, and then 20 for my width, and then I say that I'm using optimized window placement, and that will just place the barriers. So we're gonna look, I think, a little bit at both. What the MacLean lab tends to do is just use this optimized window placement, which puts the window boundaries at places that are the most unlikely to have charge 2 and charge 3 peptides. If you really want to measure higher charge states, actually charge 1, 2, and 3. So these are optimized placement of window boundaries so that they're as far away as possible from charge 1, 2, and 3. And if you want to do higher charge state, then you probably really should use some kind of border, some kind of margin. You can see here there's a field for margin width, and a typical one that like the aerosol lab uses a fair amount would be to put a margin width of 0.5. But with optimized window placement, we found in the MacLean lab, we don't need that. So they're far enough away that we don't get the signal drop off that's described in the paper, the original swath paper. So we go click OK here, and now you can see that the boundaries are all these weird numbers, and there, it turns out that molecules are built out of atoms, and atoms have certain. It's like building. Jarrett used to say it's like building Legos. It's building a building out of Legos. There are certain units, and you're not going to find something 3/4 of a Lego in size. So that these are well optimized. Although charge state changes where things fall, and so if you get up to higher charge states, these won't necessarily work. Okay, so that's it. That's what I would do. Now I've got this optimized window placement, and because I'm starting with the most naive use of Skyline for DIA, and it works. You can do it, but you won't necessarily be very happy with it in a lot of cases, and unless you do have purified sample. This is not a great way to go, and in fact, we now turn the text to red, and if you hover over it, it says full gradient chromatograms will take longer to import, consume more disk space, and may make peak picking, oh, that went away too quick, less effective. So we're warning you, hey, this is not what we would recommend. In fact, there are two other options that we're going to look at. One is to use MSIDs from DDA, and the other one is to use retention time prediction with IRT. And those are highly preferable. You can go ahead and just do full chromatogram extraction, and it may work for you in certain cases. So let's see, what else is there? And then we want to go to, so in instrument, maybe we raise the range up to 1800 or 2000 is typical for these instruments. We're not actually going to use any kind of library, so we'll leave that. And then here, I'm going to say 2 and 3. I'm going to stick with ion charges 1. And remember, I'm doing this without any library. So, and then I say YBP. So I'm going to measure all Y, B, and P. And then I would say maybe I'm going to use ion 3 through last ion, and I'll turn this off. And maybe there's an option to exclude things in the DIA precursor window, which can be useful, and the aerosol lab, I think, does this a fair amount, but we're going to turn it off for this tutorial. So that would just be, I have no idea about these, I have no prior knowledge here. I'm just going to go looking for my proteins, right? And then, yeah, all this stays the same. And so then if I go to peptide settings, I think peptide settings will be just fine. Maybe, yeah, I'm going to leave no miscleavages. I'm not doing any sort of prediction. The filtering is fine. Library modifications are blank. So if you had anything prior, you'd want to set things back up like this. And one quick way to do that is also you could choose settings default here to get yourself all the way back to default settings. And we're going to go quickly add a background proteome. So if I go to peptide settings, there's this concept of a background proteome, which is just a database built off of a FASTA file. It gives us more information about a FASTA file. And in this case, I already have one built, so I'm just going to go quickly add it. And I can open it, and that is on my USB drive. In the pub CelebSec 2015, there is a CelebSec yeast forward and reverse that's already built. Skyline will load it and tell me that there's 13,263 proteins, and it's actually got forward and reverse. And yeah, we'll just leave the name the way it is here. So it's for yeast, 6,500, about 6,500, 6,600 proteins. And we'll click OK. And so yeah, so there it is. That's my settings. And then now, because I've got the background proteome, I can just insert proteins by starting to type pyruvate decarb. So that's probably decarboxylase. I know you can see I'm getting the reverse ones too. So I would really probably rather have a background proteome that didn't have the reverse ones. But in this case, I want this first one, YLR044C. And there it is. And you can see I get a number of peptides, and some of them have, like, this one has a charge 3 precursor. And it's all charged. That's charge 2. And so why not charge 2 here? Does anybody know? Why am I limited to charge 3 precursors? And even some of these really longer ones, I can't even get anything. What? No, we don't have any prior knowledge about it. Yeah, somebody got it. Who said outside the range, right? So we told Skyline, I'm only going to measure 400 to 800. So Skyline's like, well, you can't measure the doubly charged form. And in fact, I think if you expand here, this filter will show you what's being filtered, and if you unclick the filter, you'll get some other options, but you don't get charge 2 or charge 1 because they're not measurable. So Skyline doesn't want to let you do those at all, but you get up to charge 4, and you could add higher charge states. But anyway, but we have already told Skyline that we want to measure just 2 and 3. So it's not showing us, the filter says, well, you didn't include charge 4, so I'm not going to show it to you. Okay, and so then, yeah, these longer ones, if I drop one of those and unfilter, now I get charge 5 and 6. Right, so in the other case, the reason charge 5 and 6 didn't show up was because that would make the precursor charge too low, right? So these are just the things so you can see 420 fits within my range of 400 to 800. So all 3 of these fit within the range, and so Skyline's doing that calculation. So if we really wanted to try to measure this thing, we could say, let's check okay, we're going to do the charge 4 one. And we could individually go down here and add charge 4s for the ones that could only be measured with charge 4. All right, and so then the next protein that we want to measure is glycolysis. Oops. and it's they call us this YC. It's this first one, right? So we just choose that. Now we've got 2 proteins, and we didn't even need these proteins. We could, we can also export a method. We should have done. I should have done that earlier. You don't need to choose your targets before you export a method. Unlike if you attended the SRM or you've done PRM, you sort of have to choose these things because you have to tell the instrument what you're going to measure. And so the instrument really cares about these precursor MZs and the product. In PRM, it doesn't really care about the product MZs, but in SRM, it does. And so if you've been working with Skyline for targeted analysis, you may be used to setting up this document before you generate your method. In this case, we could just go File, Export, Isolation List, and we could have done this with no, we could do this just fine with no precursors. So I could go back to here where so now I have no precursors, and I can go File, Export, Isolation List, and I can choose to export to a ThermoQ Exactive single method, and I click OK, and I'm going to write it just at the in my DIA intro, 2 proteins, and I'm going to call this 20, or I guess 800, 400 to 820 MZ. And so that's my isolation list. If I go look at it, here it is, and it's really quite simple. It's just a list of centers, right? And so somewhere in the method, I'm going to say, hey, I want 20 MZ windows, and then the method's going to use these centers as the windows. So this is how you would set up a ThermoQ Exactive for this DIA. There's no information here about what I'm targeting, right? Okay, so let's quickly go back to, so now so that was our, this is our method here. If I now redo all those steps, that's essentially the method that we would now like to extract out of the data. We're not going to do that. We're going to do that together, but we'll take a quick look at what this looks like, because this is your completely uninformed, and we're going to progress from this. We're just going to open anyway. We're going to progress from this sort of completely uninformed way of starting with DIA to adding progressively more information from various sources and seeing how prior knowledge and more information helps us. So here, if I look at this first peptide, it's kind of hard to see because, wow, Skyline picked this thing, and there are all these really big things, and, some of them maybe even look kind of nice. That thing, that's got probably similar, some similarities to my precursor of interest. This one actually maybe 2, although it's got 16 ppm off. So why did it choose this little thing over here? And that will become more apparent once I do, once I switch to transition split graph. So that splits up my transitions, and now I can see my precursors and my fragments. The fragments were so low intensity that if I don't do split graph, then, trying to see what's going on with the fragment ions, even in this one that got picked, this purple, these blue, purple, and brown, those are the precursor, right? You can see that is the monoisotopic, the M+1 and the M+2. And then down here, those are the fragments, and they're kind of hard to see unless I do this transition split graph. And now I can see that, oh, okay, well, that's why I chose this peak, because it's got 4 nice co-eluting transitions, 2 ppm, and this is 0.3 ppm. So this is so this says that the isotope dot product is 0.55. Is that a good isotope dot product? Do people understand that? I talked about it a little bit yesterday. Do people understand the concept of the isotope dot products? What is the isotope dot product? Yeah, it's a match to theoretical, and actually we can see that by going to view peak areas, replicate comparison, in here. Now we'll get, this is the theoretical distribution, the expected distribution of this, and why am I getting 0.55? Because I'm really only measuring monoisotopic, and that tells me that the settings here, I need to turn on integrate all, because Skyline is just going, well, these, and I don't know why it's doing this. It seems to be thinking that these two things are not well colluding with our primary one. But so in a lot of cases, integrate all is sort of something that we're going to try to get rid of this as a requirement, make it more a visualization thing. But integrate all, most of the time you're going to want to have it checked unless you're actively trying to decide which transitions to measure, and then whether or not they collude may make some difference. But anyway, so here's our isotope dot products. Why don't we have any expectations of our product ions? What? Yeah, because we don't have a spectral library. Okay, and who can tell me which product ions are actually colluding here? We got Y6, and we've got B3, and we've got Y3, and we've got Y5. So that's pretty good. Having Y6, Y5, the B3 and Y3 are not as much good evidence as Y5 and Y6. And why is that? What? Yeah, they're not very selective, and especially if you think about those highly chimeric DIA spectra, that's not a lot of evidence. It's not giving me a whole lot more evidence than my precursor. But yeah, my precursor looks great, right? So this is a really nice spectrum. Skyline just chose this out of the blue, and we might definitely go, okay, this, I feel like I measured my protein here with this peptide. So now how about this next one? Where Skyline shows this, but there's no site, I don't see a precursor. There's this thing over here, but it's 60 ppm off. This one is even 20 ppm off, which I don't really expect out of an Orbitrap. And if I were using, the extraction would have been totally different if I hadn't used Orbitrap extraction. If I'd used centroided extraction, I wouldn't even be able to see something that was 60 ppm away from my. But anyway, so I don't really see anything here. But this is, full. If you're trying to figure out whether you can see things, actually having the full gradient extracted can be really confusing, right? It's like, it turns out that Skyline does a pretty good job, and there won't typically be a whole lot of other things than what Skyline picked, but it's really hard to know. And this thing, well, is this it? Well, it's 40 ppm off, and yeah, I guess the isotope dot product's not that bad, but anyway, so you can see that this would be really challenging. If I were to go through here and look at every single one, I can press F11 and just zoom into what Skyline chose. This is another really nice one. So you can imagine that this is a great one, right? It's charge to isotope dot product at 0.1 pp, very very low ppm off, and it's got a ton of colluding ions. So you could probably come up with a set of things to measure for this protein, even though we've never seen it before, right? That maybe is one too. But anyway, so now let's go and see. Well, actually, I guess we're running out of time even. So, well, any questions? We can pick this up later, and we could go. We can. The rest of this section is to actually use some DDA data to inform ourselves better. But you can see that you can figure out some of these things, and there are tools that have emerged now that can find this type of match in DIA data. So this is what DIA umpire is going to do automatically, is to find these matches of precursor ions with product ions. Yeah. But the minimum number to keep? It really depends. So what we're going to show you statistically is, like, when we do large-scale statistical analysis of DIA data, we like to have about 6, and that's what was written up in the original swath. Paper, but really for an assay, right? A clinical assay, you look at there's a clinical assay coming out of the Hufnagel lab to measure thyroglobulin. They get down to 1 transition, right? And if you have enough prior knowledge, that's fine. So you only need 1 transition to quantify by. If you know that transition is highly selective and you know exactly where it elutes, a targeted experiment can rely on 1 transition. But statistically, if you're going to throw it in with a whole, thousands of tens of thousands of other things, then statistically we think you should have 6 or more. Although, yeah, actually, there's some software where the default is minimum is 4. You guys use just 6 straight through, right? Yeah. There's issues of whether or not you can use neutral loss ions. We tend not to, but I definitely see assays with neutral loss ions, and then I think Christy Hunter from SciEx was saying that they have some rule. They actually allow neutral loss ions, but they have some rules, because I definitely, actually, the Bruder paper, I was looking at some of the sets of transitions that they use in the Bruder paper, and there clearly they were pressured to have a really big number because they're competing with DDA. So the bigger number, the better. So, but I was looking at some of them, and I found one that was like, okay, it's really two fragment ions, and then 4 different neutral losses from those fragment ions. And I'm like, well, okay, that's not really a whole lot of evidence of the peptide that you can find 2 fragment ions and then 4 neutral losses of those fragment ions. So, yeah, there's still a bit of that's still being developed, exactly what transitions to use. Yeah.
But when my machine is to have the variant like 6 to 19, so we can change here as well to make it variant kind of stuff.
Yeah. You can have variable windows. Yeah, and that's always an option. We haven't done a whole lot of that with Thermo Q Exactive. I think our lab is still doing fixed width, but we do overlapping to get narrower windows, and Mike will talk about that. But yeah, I mean and actually the Bruder paper, when we look at that, that's a gradient. Actually, I think now Celebsec. So we're going to look at data from 2 papers. One is using SciEx data, and that's Celebsec, and it was done in early 2015, and then later 2015, the Bruder paper came out from Diagnosis, and that uses a variable gradient. That uses a variable window scheme on a Q Exactive, and then all the time now, pretty much everybody is using variable windows on a SciEx instrument, triple top. So SciEx has, and there are some built into Skyline. If you look into settings, transition settings, we kind of ran right by this, but in full scan, we've got some isolation schemes in there, and Skyline has some default ones, and these 2 are fixed windows, and these 2 are VW64 and VW100 are Christy Hunter's favorite variable window isolation schemes, and so, she might be able, I think maybe one is good for plasma and others are good for cell lysate. Maybe the 100 is for cell lysate or something. I don't know. But, and then 25 that's what was originally published in the Gillet paper for swath. But these have fallen out of favor. These are definitely the ones to use. The Navarro paper, we definitely showed that there's an advantage to using variable windows, and they are usable on Q-Exactive as well.
In case of fusion or reverse, would you get a high resolution or anybody has experience already on?
Yeah, I mean, I'm not the person to talk to, but we definitely have presentations from Jared Eggertson, who's done a lot in our lab with the Q-Exactive, and he certainly has favorite. I mean, you're always playing with higher resolution, with increases your scan time, and so what he will say, he actually has graphs where he's shown that like if you don't use high enough resolution, there's an Orbitrap takes a certain amount of time to do a scan, and so it's fill time. You want to have the optimal fill time for your scan time, and so all that stuff has been worked out, and there are presentations explaining that online and stuff. So, all right, I'm gonna turn things over to Ben because we're about at 9 o'clock.